Okay, welcome back to a new physics tutorial. In this video I would like to explain how you can derive the so-called Schrödinger equation. And the term derivation is a little bit problematic because you can actually not derive it from any first principles, but I will show you now that the Schrödinger equation follows naturally, so to say, if you assume that you can describe particles with the help of wave functions. And before we start, let me briefly note down the Schrödinger equation in the way how you might seen it before. There are few different ways how to write it down. So the one which I know is that we have here a minus h bar square divided by 2m, and then we can either use this Laplace operator, or if we only take one dimension into account, then we can just write here d square over dx square, which is the second derivative with respect to x. And I use this partial d's here because our wave function is a function of x and t. So in this case, we only calculate the derivative with respect to x. And then we normally add a potential here, which we call v. And then we write down brackets here. We put this in parentheses. And then we can write down psi of xt, our wave function. And this is equal to a h bar d over dt psi of xt. And this is a typical way how to write it down. This is the so-called time-dependent Schrödinger equation. If you have the time-independent Schrödinger equation, this second part on the right-hand side, this would vanish, and we would only have the eigenvalues e psi xt standing there. Okay, now let me give you some ideas how to derive that. Now, the first thing which we will use for that is one of the most fundamental laws in physics, and this is the so-called energy conservation. This is also our Ansatz. So we write here E is equal to the total energy of the particle is equal to the sum of the kinetic energy T and the potential V. And now let me also add one other function here, the so-called wave function, psi, because when we write it in such a way, then we can replace the total energy and the kinetic energy with operators. We cannot insert here because we just don't know it. It totally depends on the external parameters, like the field in which the particle is located. But the total energy and the kinetic energy, of course, this we could calculate. And in order to do that, we want to start actually with the kinetic energy. And in order to do that, we need to find the operator for t, and for this we have to find the connection between the kinetic energy and the momentum. So let's write it down in this way. Kinetic energy of a particle is given as, of course, 1/2 mv square, as you might know it. And then you also know that the momentum for classical, all this is done for classical physics. If you go to relativistic physics, you cannot use the Schrödinger equation anymore. So we stay in the classical limit. So we have here our p, the momentum, equal to the product of the mass of the particle and the speed. And if we insert this here into our, we insert here our v into our equation for t, then this leads to the very famous correlation between t and the momentum, which means the kinetic energy is given as p square over 2m. And in classical mechanics, maybe you have seen that already. Now we have a connection between p and t. And now the question is, of course, in quantum mechanics, what is p? The momentum. And for that, we have to take one thing into account, and this is the so-called de Broglie wavelength, which means that the momentum is equal to the Planck constant divided by the wavelength of that particle, lambda. And now this is already nice to see. However, in our wave function, maybe I can write it down, how a typical wave function looks like. And this is the most general way how to write it down. Psi x of t is equal to any constant and amplitude, psi 0, let's call it, times e to the power I kx minus omega t. Now, this is a typical way how to write down a wave function. Maybe I can make one time another video about that to explain why it looks like that, but this is the way how in quantum mechanics you usually write it down. So now what you have is here a constant k and a constant omega, and we want to find out how to get the momentum and the energy from this wave function. So we need a relation between the momentum p and this constant k. So what we do normally here is to write down k. So maybe we can do it here and see how it is defined. So k is equal to 2 pi over lambda. And now what we can do, we can take our lambda here and replace this lambda in our momentum with this lambda. And then we find out that this is actually, this momentum is equal to k times h divided by 2 pi. And this we know already. This we can replace directly with h bar. Yeah, h divided by 2 pi is the so-called reduced Planck constant, and this is h bar. Yeah, so now what we get is that our momentum is equal to h bar k. This is just another way how to write it. This is just the de Broglie wavelength, but now we have a dependency of k, and now you can see how we can get the momentum from our wave function, yeah, in the form of an operator. So what we have to do, we have to actually calculate the derivative of our wave function with respect to x, and then our k will can be taken out, just because taking the chain rule of calculus and differential calculus into account, and then in this case our k can be isolated. So let's do that. So let's calculate d over dx of psi of xt, which is of course equal to d over dx times d over dx of psi 0 times e to the power I kx minus omega t. Yeah, and this is easy. As I said, we have to use the chain rule, and this e function does not change. Yeah, so e to the power x, the derivative with respect to x is just e to the power x, but the inner derivative is just our k here. Yeah, so we can write down that this is and of course I. Yeah, so I times k we have to take out, which means this is equal to ik psi 0 e to the power I kx minus omega t. And now you see this part has not changed, as I said before. So what we can do now, we can just take this part here and replace this again with psi of xt. And now, as a result, so from this it just follows that d over dx of psi x of t is equal to ik psi x of t. In principle, we could cancel out our wave function now, but it's not possible because this is an operator, this d over dx, and you can only apply this to a wave function. Otherwise, it would not work. Yeah. And now we can go back and take a look at our relation between p and k. And if we replace now k with the momentum, we would get the following result. We would actually get, so what we do, we replace here our k with p, and then what we get is that d over dx psi x of t is equal to I divided by h bar p psi of xt. Yeah, and now we can just define p as an operator, so we don't have to write down the wave functions anymore. We just write it down as an operator, and then the only thing which we have to do is solving this for p. Yeah, so what we have to do, we have to calculate times h bar, and we have to divide by I. Yeah? And now we have to take into account one additional law regarding complex numbers, and this is the fact that 1 over I can be also written as minus I. You can easily prove this. Yeah, so it's not a big problem with the rules of complex numbers, as I said. So taking this into account means that now when we solve this for p, that the operator p is given as minus I times h bar times d over dx. So this is now our momentum operator. Yeah, and this is very nice, because as we have seen before, maybe I can just write it down again. Our kinetic energy was given as p square over 2m, yeah, which we have derived in the beginning. So now what we can do, we can now insert our p into this t operator, so to say, and this then gives at the end the relation. We have to see this minus vanishes, of course, because minus square is just plus, but our I squared gives again a -1. So now this leads to minus h bar square divided by 2m. Yeah, and as you can, and also of course we have to note down the derivative with respect to x. And this has to be also squared, because we have here p square. So now, if you remember correctly, so the result that we got here, this minus h bar square divided by 2m and so on, this is exactly the term that we have given here. Yeah? So this is now our t, the same t that we have noted down here. So this, of course, if this is t and this is v, then this has to, of course, be equal to the energy, E. And now the question is how we can get the energy from the wave function, the total energy. And for that we start with maybe a new page, and the energy, this is of course always given as the Planck constant times the frequency, times nu, or you can also call it f, of course. And now we want to get a relation between this omega in the wave function that was given here, this omega in the wave function, and the energy. Yeah. So what we do, we can replace actually nu with the angular frequency. Yeah. So we can say omega is 2 pi times the frequency nu. And if we insert this into this equation, we actually get as a result h omega divided by 2 pi. And of course then we can shift this 2 pi, which gives again the reduced Planck constant. So at the end this can be just written as h bar times omega. And now you can see exactly what we have to do. If we want to get this omega from the wave function here, we have to calculate the derivative with respect to t. Yeah. So now not with respect to x as we have done it before, but with respect to t. So we can write d over dt of psi of xt. And this is then also simple when we go back to our wave function. Again, our we can isolate our I, we can isolate our omega, including this minus here, which then leads to the fact that this is minus I omega times psi 0 e to the power I kx minus omega t. And again, this is our psi of xt, as we have seen it before. So we can say that the derivative of psi x of t with respect to t is minus I omega. And if we insert again this e, this function here, e is equal to h bar omega, into that. So again, I can maybe highlight this here and here. Then this leads to the fact that this is equal to minus I e divided by h bar times psi x of t. And again, e is an operator because it's the derivative of the wave function with respect to t. So if we solve this now for t, again we have to divide it by minus I, which leads to the fact that in this fraction which we get, the minus vanishes, and we have to multiply it with h bar, and this leads to the fact that e, the operator e, is given as I h bar d over dt. And again, when we take a look, we get now here our new formula, our new function, our new operator equation, so to say. And this is exactly also what is given here. Yeah. So so of course the energy is not this full term here. Maybe I can delete that. The energy would be only given as this part here, E. Yeah, so now what we can actually see from this very short derivation, so to say, although it's not a derivation, is that the Schrödinger equation can be derived from the fact that particles can be treated as wave functions, and just from the ansatz of the energy conservation, yeah, by taking E, T, and V, the potential energy, the kinetic energy, and total energy, into account. However, there's one fact about the Schrödinger equation which many people have never thought about, maybe, and this is the fact that this is always called wave equation. Yeah, but actually it's not a wave equation. When you take a look at how the wave equation is defined, then you will see that we have the second derivative with respect to x, but we have also another second derivative with respect to t, which is not the case for the Schrödinger equation. So in this case, you can see that the Schrödinger equation is not a wave equation. Yeah? It's actually an equation which is connected to the thermal heat conduction, which has nothing to do even with quantum mechanics. However, historically it is called wave equation. So until now, people are using this word. Yeah, this by itself is a very complicated topic, so I don't want to go now into that, but I will just mention this, and maybe I can make one day another video about that to clarify this. Yeah, and with this I want to stop now here. Yeah, we have now seen a very short motivation, so to say, for the Schrödinger equation, and I think it was very instructive, hopefully, and it also gives you a better idea what you are doing when you use the Schrödinger equation. Okay, and also why, for example, when you solve it for the infinite potential well, yeah, you get these kind of eigenvalues that you are getting. Yeah? And I have also made another video about this. If you are interested in this, you can have a look at it. Otherwise, I would stop now here. Thank you very much for your attention. Thank you very much for opening the video. If you like the video, as usual, I would be really happy if you like it. If you click the like button, if you subscribe my channel, if you have not done so far. And otherwise see you soon for another video.